So I'm back. I'm just realizing, going through my notes, that we actually use Biosavar quite a bit. So I maybe was letting you know. I think I was putting more emphasis on Ampere's law than I should have. So Biosavar, learn it, love it. We're going to be using it quite a bit. Okay, so getting back to our wire situation, we've got that our B field, and we can say the net B field. I'm going to say the net just because you'll see in a second why. We've got mu naught over 2 pi r. And what I could do instead of big R, let's do little r, because we want to do the distance away from whatever we are. And then, excuse me, of course, the current that is going through it. So for one wire, that's what we've got, okay, if we had just had one wire. But what if we have a whole bunch of them, okay? And we'll just fill this thing up. It's common to have cables that have bunches of wires in there. And who knows how many are in there? You could have counted them if you wanted, but at any rate, let's say we have N. Okay, so we've got N wires. And of course, at some point P, there's a distance. So let's choose this wire right here. That would be Rn, or I shouldn't say Rn, that would be Ri. All right, for just one of them. And we will go, we'll say, well, each one of these guys has a current. Now, who knows what the current is in each one? So we don't know. So then we're going to get this equation where we say mu naught over 2 pi times some sum. And our sum is I equals 1. So let's say this is number 1 right here, and this is number n right there. I'll color in 1, I'll color it in blue, and I'll color n in blue. And then you just count them, right, all the way along. And we'll go from I equals 1 to n, and that's what we get. So it's a superposition of all the B fields from all of the wires that are in the main cable. Okay. All right. So we have figured out B due to a wire. Okay, so we have one wire, and it's got some current. We'll call it I1. Let's draw our X and Y's here. And we have some P perpendicular. And we know that there's some B field. So I'm going to say B field at point P due to 1. What is the B field? Well, that's B1 equals mu naught I1 2 pi r. And of course, that is our r. Okay, so what if we put another wire perpendicular, completely parallel, and we send it in with some y or I2 at that very distance, okay, r, right through our point. The two I1 is parallel to I2. And the whole goal or the whole question is, what is the force on the second wire? Wire number 2. And of course, this is wire number 1. Wire number 2. So what is that force? What do we use to do this? Well, F equals ILB. Everything's perpendicular to each other, so, right? So if everything's perpendicular, we're multiplying by the sine of 90 degrees. So we don't have to worry about that. And that's what we're going to use. So the force of 1 onto 2 is equal to I2 LB1, okay? So I2 LB1, but we just figured out what B1 was. So let's put that in there. So we've got I2 times L times mu naught I1 over 2 pi r. Now we can make r the distance between the two wires, because that distance is going to stay constant. So we're going to keep that. So we can make that distance, whatever, r equals d if you want to think about it, but we let's just leave it at r and rearrange and divide by L. Okay, so we'll have a force per unit length. So let's get a little more space here. So we'll have a force per unit length, and our F12 per unit length is mu naught over 2 pi I1 I2 over r. And then we can put that in the books. But this makes things a little bit more interesting, because everyone loved the work of Biot Savart, right? And so they're like, well, man, what can we do with this? We can do some stuff here, especially the French. They love units and all those things. So Newton's third law. And hopefully you guys are saying, oh, I know exactly what Newton's third law is. Well, because I would be asking you, what is Newton's third law? And you would say, it's the fact that we have forces that are equal and opposite, right? So we know what F12 is, and that means that the force of the second wire on the first wire is going to be equal in magnitude but opposite in direction. So let's get into that. Let's first figure out what F12 is. So let's go down here, figure out the direction of F12. So we have a B field. What's our B field? So we put our thumb along the current I1, because we want to know the direction. We want to know the direction. Ugh, what is going on? We want to know the direction of this, okay? So what direction? Right-hand rule. Put your thumb along I1, curl your fingers around till you have them at P, and you'll notice that your fingers stick up out of the page. So B1, boop, boop, boop. That's into the page. We want out of the page. So B1 is sticking out of the page, and if that's X, Y, and Z, X, Y, it's actually K hat. Okay, positive K hat. That's our force. I'm sorry. That's our B field. Now, what is the force? Well, that's IL cross B. So let's get back to our force. So IL cross B. I2L cross B1. I2 is going in that direction, so you put your fingers along that direction. You cross that with B, and you'll notice that our force then, I'll do the force in green, our force is going in this direction. Play around with that a little bit, but the cross product is found here and here, and put your fingers along I2, bend them toward B1, and you'll see your thumb pointing in the F direction. So that's our F12, all right? That's F12. So F12 points in negative X. Negative I hat. That means that F21 should point in positive I hat. All right, so the force of the second wire on the first wire should point in I hat. Should we just rewrite the wires here? Okay. F12, F21. What did we just find out? Well, these two wires are attracted to each other. Why am I not what is going on in my brain? Attracted to each other. All right, so I want you guys to go through and do the same thing, but this time you can change the direction of one of the currents. So it doesn't matter which one you choose, but let's choose I2 just for demonstration purposes, and we're going to say that I2 is going up and I1 is going down, so I1 is anti-parallel to I2. In that case, the two wires are repulsive. Repel. Okay. So, there's one other thing to this. Okay, there's one other thing. Like I was saying earlier, the French love the units. They're the ones who hold all the unit things going on and this, that, and the other. And if we make infinite wires, okay, 1 meter apart, so R equals 1 meter, and we put a current of exactly 1 amp through each. So I1 equals I2 equals 1 amp. And we want to know the force per the unit length. We will get 2 times 10 to the minus 7 newtons per meter. So you can measure the force, and when your force gets to a point where it is equal to this, when you measure this as your force, then you know you are putting 1 amp through each of the wires. This is the definition of 1 amp, okay? So here's how it works. So what do we have? We have 2 times 10 to the minus 7, and that equals our mu naught 2 pi I, and they're both the same, so I'm just gonna say I1 squared. And we have our 1 meter on the bottom. We can solve that for I squared, I1 squared, and then take the square root if we want, but 1 squared is 1. So even if we don't take the square root, we should still be okay. And we end up with 4 pi times 10 to the minus 7 over 4 pi times 10 to the minus 7. And then our units are, let's give myself a little bit of room here. Our units are amps times newtons per, but this whole thing is also amps, so we end up with amps squared. So we say that this cancels with this, and we end up with 1. So our I1 is equal to 1 amp, because we're going to end up taking the square root of all of this and showing that I1 is equal to 1 amp. So that's how you know you can measure this, and then you dial it up or down until it equals that. And once it equals that, then you know you have exactly 1 amp going through your wire. Okay. What about the B produced by a current loop? So we're going to do current loop, and we've got our current going in and out, and here's our loop, radius R. what are we going to do? Now imagine this is a very small section of our loop, okay? Negligible, the little gap between in and out here. So there's our current going in, here's our current going out. We're gonna say we've got some DL here. We wanna know at point P what's happening. And so this isn't a great picture because that's the R. It's not a great picture because it's hard to draw 3D. And what I'm trying to show, and I will in a second, is that this P, this point P, is exactly down the center of the where the radius is. So how's a better drawing? How can we do a better drawing? So here's X. Here's Y. And X cross Y is going to give us Z. And we're putting our point, say, right here, and our circle is in the XY plane, like that, with some R. And we're just going to do this, okay? So maybe a little bit hard to see. So this is our K hat. Maybe a little bit hard to see, but at this point, we're going to get a dB, okay? And dB is exactly perpendicular to the RDL for right here. So it's exactly perpendicular. So that means that dB is pointing in this direction. And then there's some theta here between K hat and dB. Okay, so what does Biot-Savart say? We're going to rewrite it. We're going to do our dB is equal to mu naught over 4 pi. 4 pi. And I dl cross r hat over r squared. So that's our Biot-Savart. We need to figure out a few things, like for instance, dl cross r hat. And notice that our dl, this is going to be equal to dl sine of pi over 2 r hat, which is sine of pi over 2 is going to give us our 1 that we need. So it's really just dl, right, times 1. R hat is perpendicular to dl. Right? Everyone knows. Good. You can see that. So now what do? We have some distance z going from the plane, xy plane, to our point P. So R is going, the magnitude of R is going to equal whatever, there's two R's. Let's call that a bigger R. And we're going to square that, and then we're also going to square Z. Yeah, better. So we've got a big R is our circle R, and then our little r is the distance from P to the DL. Too many R's. So now what do? We plug in these things, right? We figured out what DL cross R is. It doesn't matter, we'll be given some current probably. We know all of these things, and we've written down what R squared is. So we can then say that dB is equal to mu naught over 4 pi IDL over R squared plus Z squared. So now we're going to integrate, right? Because we want all of the DLs. So we're going to end up integrating, and we're going to say that B is equal to our dB cosine theta all along the wire loop I'll tell you why the cosine theta in a second. Anything that is the sine, dB sine, of theta, all of those contributions are going to cancel out because we're going to go all the way around the loop. So the sine of theta, if we add all of those things up, we're going to integrate from 0 to 2 pi. We're going to end up with 0. Okay? So none of the contributions in the sine direction. So let me draw a little. Here's our point P, here's our dB. And here's our theta. So this is dB sine theta, and this is dB cosine theta. The only things that are going to contribute is dB cosine theta. All right? So this integral on one side is going to equal our thing, okay? This is our B. So what does that mean? We're going to then say B is equal to our integral of dB times the cosine of theta. So I'm going to put in dB. Here's my mu naught. It's a 4. It's a 4. Four pi and I dL R squared plus Z squared cosine theta, and this is over the wire loop. Cosine theta in the k hat direction. Now, the current is going to be constant, all right? Mu naught is constant. We can't really separate R squared and Z squared, but those are also constant. Those aren't going to change. So we really are technically left with some stuff. Now, what isn't constant, how do I want to do this? What is cosine of theta? And we want to have cosine of theta in terms of r and this r and this r. So what is the cosine of theta? Well, this is theta here. So is that theta? That's not theta. That's phi. Sorry. That is not theta. Theta is here. So it's hard to see, but that's our theta. So now r cosine theta is our radius. So let's slide up here a little bit. So r cosine theta is the radius of our circle, and therefore we can say that the cosine of theta is equal to big R over R. And we already know that R is we know what R is. We figured it out earlier. That's this. So we can say that's R over R squared plus Z squared to the 1/2. So we're going to plug that in. That's our cosine theta. I'm going to factor out all the constants. I don't even want those in there. What else don't I want? Let's see. What else don't I want? Oh, I need an R for the top part of cosine theta. And then we're going to do on the wire loop, we're going to go all the way around it, and that'll be dl in the k hat direction. So we're going to go from 0 to 2 pi r all the way around it. So that's what this bit is going to equal, 2 pi r. And b is equal to mu naught I r squared. We're going to cancel out the, where did my 4 pi go? 4 pi. We're going to cancel out our pi. Pi on top. And so we'll be left with 2 z squared plus r squared to the 3/2 in the k hat direction. All right. Now, earlier we said that mu is equal to our current times the area in the n hat direction. And the area of this thing, everyone should know, is pi big R squared. So give ourselves a little more room. I times pi R squared in the k hat direction equals mu. And that gives us mu over pi is equal to I R squared. Of course, this isn't the resistance, okay? This is R is the radius of loop. All right, I know it looks like power, but it's not, because that's also I squared R, but whatever. So R is the radius of the loop, keep that in mind. And we can then put in our stuff. N hat is equal to K hat, so that's good. They're in the same direction. So we can rewrite everything as mu naught, and we need to get our pi back. So here's our pi. We're putting our pi back in there. So we've got our 2 pi. We're going to do z squared plus r squared to the 3/2. And we've got on top our magnetic moment. All right. Now, we can do z equals 0 to find b exactly in the middle of the loop. Okay, so I'm going to draw our loop. Here's our z direction. So here's z. And basically what I'm doing is I'm saying z equals 0. And that is the middle of the loop. Z equals 0 right there. All right. So what do we get in that situation? B equals mu naught I R squared over 2 times 0 squared plus r squared to the 3/2. Oh, don't let me forget my k hat. And all of a sudden some things cancel out and we're left with mu naught I over 2r in the k hat direction. And that's our B field in the middle, right? And this is the same thing that you end up when you do Ampere's law. All right, so that's very nice. Now, of course, we can do n loops, right? So we can have this thing come in and it'll go around and around and around n times and then come back out. So our current goes in one side, comes out the other. And it could be n different loops. So our B field in the middle, right in the middle of our circle, ends up being B n mu naught I over 2r in the k hat direction. All right, now we've got one other thing that we can do. Keep in mind, this is the equation that we want to work with right here. And we've got one other thing that we want to do. So I'm going to keep that equation at the top. And that is, notice what happens when z is super large compared to our radius r, okay? So I'm going to rewrite this because I want to move up and get some space. Okay, let's move up. So what happens? Well, z equals much greater than r. So we're going to go like this, and we'll end up with mu naught mu over 2 pi, and then we've got z cubed, because the square gets rid of the 1/2, and that's our b. Like that. And this is our magnetic field due to a dipole. Now, do you notice that there really isn't a dipole? It's just this. Okay, that's it. There's no dipole, all right? So this generates, just like an atom, iron atom, with its cloud going around the atom, doing some current in this direction. It's the same thing. We've got the current going in this direction. So what does that give us? That gives us some magnetic field like this, okay? So this would be what, what we would call our magnetic moment. If I were to draw this circle in more of a flat way, then you could see that the B field does something like that. And that B field comes from the magnetic field from a dipole. But is it really a dipole? No. But we call it a dipole because that's what's generating our B field. It's dipole-like, right? So our magnetic moment is dipole-like, all right? So we call it a quote-unquote dipole, but no poles in real life, okay? IRL. All right, so the next thing. We, how do I, no magnetic monopoles. And so I don't know if any of you guys are into it, but there's the search for magnetic monopoles. People are searching for it all the time. And all they really find are currents flowing. So good luck to those people. They're still looking. Everybody's looking. Not everybody. A lot of people like myself have given up. So we talked about creating a uniform B field. And when we do, we create this B field like this. So we have all these, it's a coil, a solenoid, and all these guys have the current flowing into the page on that side. On this side, we've got the same thing happening, but these guys are flowing out of the page. And so you can put your thumb along the wire. Let's have our wire go like this. Okay, so our current is going in this direction. So you can put your thumb along the current and move your fingers until you get to the B field itself, and you'll notice that our B field is going in this direction. And it's a uniform B field because we're saying this goes to infinity and this goes to minus infinity. So our B field is uniform. What is the B field? So it's mu naught n I k hat. And n is just your number of turns per unit length. Okay, so we'll put some length up here. And so your number of turns per length is your n, and you multiply by mu naught and your current that you got going through it, and this is your B field in this situation. Now, you could rewrite it, right? You could say, okay, well, that means that B is equal to mu naught n over L times I in the k hat direction. L up there. The technical name for this is a toroidal. How do I spell toroidal? Solenoid. Okay. And we've got some in the class. Now, why? Okay, I don't like the L. I don't like the L thing, but let's go like this and say that there's some circumference L, okay, about our solenoid. So all the way around from one side to the other, we've got this solenoid L, okay? And big L is equal to 2 pi r. And if we I don't like this. I don't like it. I'm supposed to get that our B field is equal to mu naught n over 2 pi r times I. the circle, the length that we're choosing has to be equal to our 2 pi r as well. So the length L that we choose this direction has to be the same as the length around the circle in this direction. So that's the only way this works. And if that's the case, then we have this thing here, which is what I want to end on. And just real quick, I don't know if you guys know about fusion reactors, but this is exactly how they keep a fusion reactor is a toroidal thing, and so the magnetic field, when this is cranked up high enough, keeps our plasma in the middle of the circle. So that it can do its thing. It can burn and whatever in the middle of the circle, and it's the plasma. I should have red or something for the plasma, but I can't see red. So okay, I think that does it for today. Thank you for your attention and time and participation and all that.